Okay, so now we're at the last part of the first lecture. I know this has been a lot of information, but BJTs are pretty complicated. And so the last topic we have is on BJT switching. And so we're going to talk about different switching states for a BJT in terms of full on, full off, and in between, which would give us amplification. And so when we have a BJT, we typically bias in what we call normal forward mode operation. And there's always a resistance. Okay, so this is normal forward mode operation where we're injecting current from the emitter into the base, and then it's collected out the collector. And we always have an output resistance. I'll touch on that a little bit more later, but this output resistance could be an external resistor in your circuit, it could be the resistance of the contact, or it could be the resistance of the P-type material here. The point is we always have an output resistance for any type of amplifier. And so if it's any one of these three things, we can take the total resistance and we will just list it as being R out, or our output resistance. Now, looking at this BJT circuit, which is in a common emitter format again, right? It's this circuit node and this circuit node, both common to the emitter here. Okay, we've got 40 volts applied to this. And so one of the things that we can start to understand for this BJT right off the bat is that the maximum current that will ever flow through this BJT would be if the resistance of the BJT itself disappeared, meaning that you turn it on as much as possible. And so if you let full current flow through the BJT, you would be limited by 40 volts dropped across the output resistance, or less than 8 milliamps. That would be the 40 volts divided by 5 kiloohms, which is the output resistance, which means that you will never get more than 8 milliamps to flow through this BJT. Okay? So, now let's start to move forward and understand some of the switching states. So let's first assume that IB is really small, like close to zero or negative. At that point, how much current flows then through the circuit and through R out? Well, if my current flow is really low because I have a very small IB, remember, you don't get collector current unless you have a base current, right? So if the base current is negative, meaning that I'm biasing the base in the wrong direction, or zero, then I know I will get almost no current flow through the BJT, right? So I'll get no current flow. Well, at that point, how much voltage drop would be across the output resistance? Well, we know the voltage drop would be zero across this, because if there's no current flow through a resistor, right, then there's no voltage drop across it. So in that case of cutoff, all my voltage drop would be across the BJT. And where would it be? Well, we know from where we started when we looked at BJTs that I have a diode here, a diode here. This is the reverse bias diode. All the 40 volts will be across the reverse bias diode. Now, what we measure typically for a BJT is we'll measure collector current versus VCE, the total voltage drop across the BJT, which includes the reverse bias collector. Okay? So, I said if we basically have a small or negative IB, there will be no current flow and all the voltage drop will be across the base collector, meaning that the total voltage across the emitter to the collector will be 40 volts. And so here I am. I've got no or zero base current, so my base currents are decreasing. They go to zero or negative. I get no collector current, so my collector current is zero on this axis. And my voltage drop, VCE, across the BJT is the entire applied voltage. It's 40 volts. This point here is referred to as Bjt Cutoff. It's where I have minimum current. Now, let's assume we increase our base current by a little bit. So I've gone not from zero, now I'm at 0.02 milliamps, 0.04, all the way up to 0.1 milliamps. You can see as you increase your base current here, you should see theoretically the same collector current appear by amplification. And so if you look at this BJT here, you know the amplification factor is roughly 100, right? Because 0.08 turns into 8 milliamps for the collector current. Now, for each increase in my IB curve, you can see for the BJT, what's our value for beta? Again, it's the same for each of these. So Here it's 100, here it's 100, here's 100, here it's 100. So basically my amplification factor is constant, which I would expect for a BJT. Let's keep going. Let's say I keep increasing my base current. There's a curve, here's a curve. Let's see what if I try to go all the way up here. You'll notice that this curve here is lighter because it means you can never get there. What happened? Well, if I keep increasing my base current, I get more and more current through this loop, right? As the current increases, eventually, more and more current, more and more voltage drop across the output resistance. And so look what happens here, okay? When I get to the point where my base current is 0.08 milliamps, my output current for the collector, in theory, based on amplification factor, would be 8 milliamps, but we've already said that because of this output resistance, the most current I could have through this loop would be less than 8 milliamps. And so that means if I go for base currents above this 0.08 milliamps, I will not get any more current because I'm limited by the output resistance. And so if we plot this here, you'll see that I run into something called saturation, where I've increased the base current such that I get maximum collector current. So the collector current maximizes. Here's the maximum it can reach, 8, right? And as I do that, all the voltage drop is across the output resistance, right? If all the voltage drop is across the output resistance, then I almost have 0 voltage drop across the BJT. And so look what happens. I increase my current, I end up in saturation, and my voltage drop across the BJT, VCE, has gone almost to 0. If you connect these 2 points here, this is called a load line. You should be doing this in electronics as well. The beauty of the load line is basically using the output resistance, I can get the cutoff point. Using the output resistance and the voltage, I can get the cutoff point. I can get the saturation point here at 8 milliamps. I know my theoretical response for base current for this BJT, and my actual solutions for this circuit will therefore be the intersections of these. And so these will give me the values for any given base current. Say I've got 0.04 for milliamps for the base current. Then at that point, my VCE voltage drop across the BJT would be 20 volts, and my collector current would be 4 milliamps. Okay? So again, this is referred to as Bjt saturation. I've reached saturation. And again, look how nicely it follows the load line. Now, you'll notice here, if we keep increasing VCE, the current will saturate. So also notice on these curves, as we increase VCE for a given IB, let's say IB is fixed at 0.04 milliamps, you'll see you start to increase VCE, the current shoots up for the collector, and then it saturates, meaning that if I put more VCE, I get no more increase in current. It seems that I get to a certain VCE level, and then the BJT is working as well as it's going to work. So why is that? Well, remember that VCE dropped across here and here is all across the reverse bias base collector. And so all this voltage drop needs to do is give me reverse bias here. Once I've got this reverse bias, the collector is collecting, it's ready to do its job, and I don't need any more voltage. And so I basically, for a given IB, I start to put voltage across the BJT, and now when I get to this point, my collector is fully reverse biased, it's ready to do its job, and if I put more and more voltage across the BJT, more and more voltage from the VCE here, then it doesn't have an effect because this is already reverse biased, and just like a reverse biased diode, it's drift current, right? Drift current is not dependent on voltage because once you've created the cliff, the carriers fall off the cliff all the time anyway, okay? So you should now be able to look at this and fully understand, why the curves work like they do here. And I've noted here that this is all minus VCB here. And so, when this is plotted versus VCE, but the voltage drop, if you looked inside the BJT, is all across the base collector, okay? All right, so let's keep moving forward, and we'll try to reinforce this with 2 more slides. So again, we've got 4 regions of operation. We've got cutoff, and saturation, and then I'm going to show you things called normal active mode and inverted active mode. Okay? So again, cutoff is where I have very little or zero base current, such that the BJT is turned off. So at that point, my voltage drop is maximum across the BJT because there's no current through the circuit, and if there's no current through this resistor, there's no voltage drop. All the voltage is dropped across VBC. And so what I'm going to do is I'm going to try to plot this on a double voltage plot here. And so on this axis, I've got voltage across the base collector. On this axis, I've got voltage across the emitter base. Let's start with cutoff here. So cutoff is shown here, meaning that the most important thing is that cutoff is when I have zero or negative current here. Well, I have zero or negative current when I reverse bias the emitter base. And so VEB will be negative. This is the negative axis for VEB. So anytime I'm down here, I'm in cutoff. So if you look at this, then why am I over here? So why is the curve over here? Well, look at VBC, okay? I've got 40 volts applied across here. If voltage sums to 0 on a loop, if this is plus 40, then I should have minus 40 here across VBC, and this is basically showing me my minus 40 volts here, okay? And so no matter if I keep reverse biasing this more and more, it doesn't matter, the voltage drop will be across here for this loop here. So it stays constant. Then I get to what's called normal active mode, meaning that I'm starting to forward bias VEB. That's what I want to do. I have actual base current in the right direction. I forward bias this. I inject some electrons, which is current flow in this direction. Then I start to get whole amplification through the device. And so this is your normal operation where you get amplification with the BJT. Okay? And of course, at this point, I still have negative VBC because plus 40 here, minus 40 here, so I get my voltage loop to sum to 0 here. Okay? Now, if I keep increasing my emitter base voltage, that means I'm more strongly forward biasing this. If I'm more strongly forward biasing this, I'm increasing the base current, right? And so if I increase the base current, eventually we said that we will get to saturation, where all the voltage drop will transfer to the output resistance, meaning the resistance of this disappears, and so I end up with 40 volts across here, and no voltage drop across the BJT. Well, look what happens here. I'm increasing VEB, and now this curve pulls VBC down to 0. That's why it goes to here, because it's VBC pulled to 0. That makes sense, because if all the voltage drop in saturation is across the output resistor, then the voltage drop across here goes to 0, keep increasing VEB and IB, and that pulls VBC down to 0. So now you can see on this double voltage plot the various modes of operation for a BJT. The last mode that we didn't talk about is inverted active, and you might be wondering what that is. Well, that's basically trying to run the BJT in this direction, which you can do, and we'll talk about that when we do coupled diode model. We'll see that BJTs you can run in forward or in reverse, okay? But we'll save that for later. So, there's different ways you could use a BJT. In the earliest days of transistors, they didn't have MOSFETs, and so they used to use a BJT between modes 1 and 3, so maximum current, minimum current, and you could use it as a logic switch. But wasn't so popular because even when you're in one state or the other, you have constant current flow through the device and power consumption, and the size of these things couldn't be scaled quite like you can with MOSFETs. So it's not used for logic. But the main use for EBJTs is in this normal forward active mode where you use it as an amplifier, and that's the dominant use you have for BJTs. And again, BJTs are so attractive because you get this beautifully linear response as you increase base current to the collector current. And so you get you double the base current, you get a double in collector current. So it's this beautifully linear current amplifier. And you're only limited to the output resistance, which with good design, their output resistance can be very small, meaning that you can get huge current flow through this device, much more current typically than you would see through a field effect transistor. Okay, so last slide and then we'll wrap this all up. And so I want to show this just one more time to help you visualize this. Again, remember, that we always have an output resistance. For the case of the BJT, the output resistance is typically, at minimum, going to be determined by the lightly doped collector. Remember, I've got P plus for the emitter, lightly doped base, lightly doped collector. The collector is lightly doped because of how we fabricate it. So when you see how we fabricate these things, you understand why it's lightly doped, and that will always give me an output resistance. And so I'm going to do the same thing where I go from cutoff to normal active and saturation and look at the voltage drops across the BJT. So here I am in cutoff. I've basically biased. You can see I put a bias on the emitter base that is actually in the wrong direction. It's been reverse biased here. Okay? As a result, my collector current through this loop is 0. I get no current flow because I'm not emitting any holes into the base, right? Well, if I've got no current, my voltage across the output resistance is 0, and all the voltage is therefore dropped across the BJT. And you can see that here, and of course it's across the reverse biased of the two diodes, which is the base collector. Then I go into normal active mode here, where I start to forward bias the emitter base in the right direction. I'm injecting electrons, which is current flow, in this direction. Okay? I start to get collector current to appear, and in this case I assume that I had enough current that I get 4 milliamps output, which 4 milliamps going through 5 kiloohms will be 20 volts. If I applied 40 volts, then I've got 20 volts here, and then the remaining 20 volts for this voltage loop here will be across the base collector. I'm in normal active mode here. Then finally, I put more and more forward bias on the emitter base. I get to the point where the resistance of the BJT disappears, meaning that it's putting as much current through it as it can. My collector current maximizes to the point where this current times this output resistance is pretty much all the voltage drop, and the voltage drop across my BJT is effectively 0. We'll skip this slide. It's on Bjt switching. It's in section 7.6. But the main thing I want you to remember, and we'll talk about this when we do hybrid pi model, is that if you try to use a BJT as a switch, you're limited by a lot of the same things we talked about for diodes in terms of switching speeds, junction capacitance, time for carriers to recombine, and things of that nature. So you're not responsible for this at this point. Before we do one last final review, I want to start to warm you up so you can start to understand what circuit symbols look like. And so if you've taken electronics, or you're taking electronics right now, you might be starting to look at various types of transistors and wonder, why are they drawn the way they are? Well, we're going to cover JFETs, we're going to cover MOSFETs, and we're covering BJTs right now. And so let's start to demystify why they draw BJTs this way. Okay? And so first off, look how the emitter and the collector are pinched in compared to a MOSFET or a JFET. And so I'm not exactly sure, but there's two reasons why this could be, why they kind of pinch in on the diagram like this. One could be because of that original point contact transistor. Remember at the beginning of this lecture, you had that slab of germanium, and you had this device shaped like this with one lead here, like this, and the current went like that. And so you had an emitter and a collector and a base. Well, maybe, and I'm not certain, maybe that's why these pinch in like that. The other reason why they could pinch in is that if you look at a BJT, the base is really thin, right? And the emitter and the collector are actually quite close to each other in contact because the base is so narrow. So possibly these pinch in because of the narrow base width. But either way, use that to help you remember that when these things are drawn and pinch in like this, that's a BJT. Now, the last thing to try to understand is, why do we have these little arrows here, and what does that tell us? Well, this arrow here is called a Pnp bipolar transistor, and that's the one we've been talking about. And the reason why the arrow points into the device is because for a Pnp bipolar transistor, the one we've been talking about, we emit holes into the base, right? They go from p-type material into the n-type base. Well, holes are a positive carrier, right? And so that is current flow from the emitter into the base. Now, look at an NPN bipolar transistor. We know that this is an NPN transistor because for that transistor, the emitter is N-type, and I'm injecting, by diffusion, electrons into the base. And so if I have electrons moving in this direction into the base, I know that that is current flow in the opposite direction, hence the arrow is pointing out towards the emitter. So this now shows you the reason why in circuit symbols you'll draw PNP and NPN bipolar transistors this way. So the last slide, this review is actually comprehensive, more than just this mini lecture, but you should be able to remember some of these things. And I've provided answer options, so that helps narrow it down for you. And so the first question, to make a BJT, we have to take two back-to-back PN junctions, but make two key modifications. What are they? Is it small or wide base width? Is it heavy or light base doping? Choose one of each of these. You should know what those are. These two modifications, the reason we did them is they increase our amplification. Okay? But what else does that effectively do? To increase our amplification, are we trying to increase the amount of required base current or decrease the required amount of base current? You should know and be able to answer that too. Now let's ask ourselves this question. Assume I have an amplification factor of 100 and I use the base wire to add 4 electrons into the base. So let's say I'm over here in my diagram here and I have 1 to start with. There's 1, 2, 3, 4. So I put 4 electrons into the base. Okay? My question is, on average, how many additional holes will be in the base at any given time? And so I'm referring to down here in the base, how many holes will exist at any given time? So if you can answer that question. Is it 0? Is it 4? Or is it 400 holes, given the amplification factor of 100? Next question. Let's say I cut the base terminal wire, and using an electron gun, I add 4 electrons to the base. So what this means, basically, is that I put 4 electrons in here, but there's no wire. So once those 4 electrons in there, they're going to stay there until they recombine, but there won't be 4 to replace them. So it's not like I keep feeding in more electrons. There's no wire. I just use some electron gun, and I go 1, 2, 3, 4, and they're sitting there, but once they disappear by recombination, they're gone forever. So I do this, I add those 4 electrons, there's no wire to replenish them, and I again assume my amplification factor is 100. Here's my question. How many holes will I collect before they recombine? 0, 4, or 400 holes? Remember, they're sitting there for a while, and so how many holes get through here before they disappear by recombination? 0, 4, or 400 holes. Now for a bit tougher question, and this shows up on tests a lot. How many holes did I emit from the emitter for this question up here? And here's your hint. You'll need the holes that are collected out the back, but you will also need the holes that recombine with these 4 electrons. So if I have the holes that get collected and I have the holes recombining, how many total holes need to be emitted to recombine and be collected? Is it 0, 4, 400, or 404 in total? Last question. If I keep increasing my base current here, larger and larger base current, my collector current will either not change, keep increasing forever, or saturate as all the voltage drops across the output resistance. You should be able to answer that one as well.